natural composition alpha is equal to phi. So let's prove this theorem. Let's prove this theorem. First, let's this kernel of phi. That's phi composition phi inverse, and we know that it's a set of order pairs on S such that x phi is equal to y phi, and phi is a morphism from S to T. This is proof. So this is an equivalence relation. It's already done. Now we put it's a congruence. So we put it's left as well as I, or you can directly it's a compatible relation. So let's choose any two. That x y comma x dash y dash belongs to kernel of phi. This means x phi is equal to y phi and x dash phi is equal to y dash phi by definition of kernel of phi. Okay. So this implies x dash phi, which is equal to x phi x dash phi. But what's x phi? It's y phi y dash phi, because y phi is equal to y dash phi. Now apply the morphism property of phi. It's y dash phi. So that means x dash comma y dash belongs to kernel of phi. So therefore kernel of phi is a congruence. Therefore kernel of phi is a congruence. Therefore kernel of phi is a congruence. So kernel of phi is a congruence. Okay. Now we define a map alpha, and we show that map is is a monomorphism, and satisfying the property that it commutes the diagram. Okay, let's define that alpha, and we denote this kernel of phi. Let's denote the kernel of phi by let's denote the kernel of phi by sigma. Okay, let's denote it by sigma. Now we have to define a map alpha from S over kernel of phi. Kernel of phi is denoted by sigma. That means we have to define a map alpha from S over sigma to T. So let's define alpha from S over sigma to T by define this map by define the map by define this map by alpha from S over sigma to T by S over sigma to T. So what are the elements of S over sigma? They are just the sigma clauses of elements of S. It's like x sigma. So x sigma alpha is equal to the image of x sigma under alpha is equal to x phi. Okay, let's define this by x phi, because x phi is an element of T. Okay, so this should be the output should be in T, and phi is a map from S to T, so that means x phi is in T. So this is the natural way to define this map from S over sigma to T. And if we define this map like that, then this implies that this map is well defined. That's simple. That's not difficulty. So let's first prove that this alpha is well defined. Okay, alpha is well defined. Okay, let's define this. First prove this. Alpha is well defined and monomorphism. Okay. So for well defined, I assume that suppose these two elements are equal. I had to show that their images under alpha are equal, but this implies x comma x dash belongs to sigma, and this implies what sigma? Sigma is actually kernel of phi by definition. By definition, so which implies x phi is equal to x dash phi. But what's x phi? It's equal to x sigma alpha is equal to x dash sigma alpha. So whenever x sigma is equal to x dash sigma, then their images under sigma are equal. So which means it's well defined. Now prove its monomorphism, means it's 1 1. So now assume that x sigma phi equal to x dash sigma phi. We need to show that x sigma is equal to x dash sigma. Okay. So let's prove first its 1 1 property. So how do we do it? So by definition it means that what's x sigma phi? It's actually x phi. X phi is equal to x dash phi. This one it's x dash phi, but this gives x phi is equal to x dash phi. It means that x comma y, x comma x dash, they are sigma related. They are kernel of phi is sigma. So whenever they are sigma related, means their sigma class are equal. This means x sigma is equal to x dash sigma. So that means sigma is this alpha is well defined as well as 1 1. So it's here alpha. So this is alpha. So image of x sigma and x dash sigma under alpha, suppose they are equal. So then the elements are also equal. So that means alpha is 1 1. And now we prove that this alpha is morphism. So that's again simple. Alpha is morphism. We use the morphism property of phi actually. Now let's choose any two elements again. X sigma, x dash sigma of alpha. This is equal to, this is here x dash of sigma by definition of the sigma column. By definition of the binary operation in S over sigma, it's equal to this. And this one it's equal to x dash phi by definition of alpha, but this is equal to x phi into x dash phi, and x phi is equal to x sigma alpha, and x dash phi is equal to x dash sigma alpha. So that means alpha is monomorphism. Therefore alpha is monomorphism. And also from the definition of alpha, you can see that the image of alpha composition. Where is the definition of alpha? You can see from the definition. Also from this definition, let's write this as double star. Also from double star, you can see from double star we have x sigma alpha is equal to x phi. But what's actually x sigma? X sigma is the image of x under sigma natural map. This is already done. It's equal to x phi, and this means it's x of sigma natural alpha is equal to x phi for all x in S. So that means image of sigma natural alpha is same as image of phi, because they are equal at every point and they are also equal at every point. That means sigma natural alpha is equal to phi. Okay. So this implies sigma natural alpha is equal to phi. Sigma natural alpha is equal to phi. And also it implies that image of alpha is same as image of phi, because they are equal. So if we choose any point here image of alpha, then that must be of this type, f sigma alpha, and which is equal to x phi. So that means that is in the image of phi. And also from double star again, image of alpha is equal to image of phi. Both the images are equal. So you can prove this as well, or you can directly apply this equation from the definition. So let's if you want to prove this, let's choose any element here. Let y belongs to image of alpha. But what's alpha actually? Alpha is a map. Alpha is a map from S over sigma to T. So that means if X is an image of alpha, it means that there is some element in S over sigma. So there exists X sigma belongs to S over sigma such that X sigma of alpha is equal to Y. But X sigma of alpha is equal to X5. So which means that this Y is also in image of phi. So this is simple. This is actually if and only if you can see. Has this equation everywhere. So this proves this theorem completely. Proves this theorem completely. Now we have one more theorem here on morphism. Let's first state this theorem. Let rho be a congruence. Let rho be a congruence. Let rho be a congruence on a semigroup S. On a semigroup S. And let phi from S to T be morphism. And let phi from S to T be morphism such that this rho is subset of kernel of phi. Rho is subset of kernel of phi. Then there is a unique morphism. Then there is a unique morphism from beta from S over rho to T, S over rho to T, such that image of beta is same as image of phi, as in previous case, such that image of beta is equal to image of phi. Image of beta is equal to image of phi, and such that the diagram commutes, and such that the diagram is this one. Its map S is a S to T is a phi, and S to S over sigma here. It's obviously a sigma natural. X is equal to rho class of X. X rho natural is equal to rho class of X, and this is your beta. Diagram commutes. Okay. So commutes means these the composition of rho natural and beta, it should be equal to phi. It should be equal to phi. And you can easily verify this. It follows from the previous theorem. You can see this. The proof is not too difficult. You can do it. So proof is an exercise for you. Proof is an exercise for you. Okay. It's not too difficult. Simple push. Now we have an application of this theorem. What's that? That I want to mention here. That application. So application is let a theorem. It's the application of previous two theorems. Let rho and sigma be two concurrents. Let rho and sigma be two concurrences. Let rho and sigma be two concurrences on a semigroup S. On a semigroup S, such that rho is subset of such that this rho is subset of sigma, such that rho is subset of sigma, then this sigma over rho, so you can define this quotient sigma over rho, which is equal to this set, which is equal to x sigma x rho, y rho, x rho y rho belongs to S over rho cross S over rho, because x rho is an element of S over rho, such that x comma y belongs to sigma. Then this is a congruence. This is a congruence on S over rho. And not only this, it's a congruence on S over rho, then I can define the quotient of S over rho by sigma by rho, over rho. I can define this quotient, and that quotient is and S over rho divided by sigma by rho, because sigma by rho is a congruence on this semigroup. So I can factor S the semigroup S over rho by sigma over rho, because sigma over rho is a congruence. And this quotient now, it's isomorphic to S over sigma, S over rho, S over sigma, exactly, S over sigma. It's isomorphic to S over. It's like in case of groups, we have, suppose we have this G by N divided by, say, H by N, like where this N is a normal subgroup of H. So this is isomorphic to, in case of groups, it's isomorphic to G by H quotient. It's like that. Both H and N are normal subgroups of G, such that N is a subgroup of H. So again, the same is here. Sigma and rho, they are congruences on a semigroup S, such that this rho is subset of sigma. Then this quotient, it's again a congruence, but it's a congruence on S over rho. So that means we have a quotient semigroup S over rho divided by sigma by rho, and that quotient semigroup is isomorphic to S over sigma. S over sigma. Okay, we can prove this theorem by applying previous theorems, because here in the previous theorem we have stated that whenever rho is a congruence on a semigroup S and phi is a morphism from S to T, such that rho is subset of kernel of phi, then there is a unique morphism beta from S over phi, S over sigma, S over rho to T, such that this happens, such that this image of beta is equal to image of phi, and such that the diagram commutes. So by applying, let's try to prove this theorem. Page number 13. Prove. Now here rho is subset of sigma. So here this rho, it's subset of sigma. This is given. This is given to us. So it means that if you can see that this one, what's that? This kernel rho is subset of kernel of phi. Then there is a map from beta from S over rho. So there is a map beta from S over rho to T, but t is here, what's t here, in our case our t is s over sigma. Actually our t is s over sigma to s over. Why our t is s over sigma? Because this kernel of sigma, because kernel of to apply this theorem, we must have this phi is a map from s to t, so that t is here s over sigma, because here this sigma natural is a map from s to s over sigma, okay, such that this kernel of sigma natural is same as sigma, okay, it's same as sigma. Kernel of sigma natural is sigma. Okay, this is the morphism from s to s over sigma. So our t is actually, look at here, phi is a map from s to t, it's a morphism, and sigma natural is a map from s to s over, it's also morphism, such that kernel of sigma natural, kernel of this, such that rho is subset of kernel of phi. And here what's given in this theorem, what's the statement of this theorem here? This is the statement, this rho is subset of sigma, but in this theorem rho should be subset of kernel of phi, but our kernel of phi means kernel of rho natural, because this is our phi in our theorem. So this kernel of phi is equal to sigma, and rho is subset of kernel of phi means rho should be subset of sigma, and it is given in the statement rho is subset of sigma. So we can apply this theorem. We have to find that phi. What's this map phi here from s to t? What's the semigroup t is here? Our t is here s over sigma. Okay, phi is sigma natural. Then we can apply this theorem here. So I can find the map beta from s over sigma to s over rho to s over sigma, such that the diagram commutes as in the previous theorem. Which diagram commutes? So first we have s. It's phi. Phi means here sigma natural. Okay, this is phi to s over sigma, and here it's rho natural from s to s over rho. Then I can find beta, such that this image of beta, okay, image of beta is same as image of phi. Phi means rho natural, such that this diagram commutes means